So first, let's go over what we were doing. If you remember, we are still looking at the boson gas this week. It will be, we will finish the ideal boson gas. So if you remember, the previous week, the previous day, we had looked at the high temperature limit. We do recover the classical result, and now we were looking at what happened, what are the corrections to that. We already know that at high temperatures, everything should be classical. And then how do we find the corrections? Well, the equations are basically this. We have essentially the same equations. The only thing we are doing is how can we interpret what kind of information we can extract. And we had seen, okay, so this was how the pressure changes. We have PV, that one is the classical limit, and we have the next correction. The pressure is smaller for an ideal boson gas. That also makes sense. It's consistent with our previous discussions that if you remember, when we study two boson system, they behave as if there's an attractive potential between them because of their indistinguishable property. So, and you quite often hear that bosons want to be together. That is the reason why we say that. There is an effective quantum mechanical attraction between them, even though they are not interacting. So if they are attracting each other, you would expect them to exert less pressure on the walls, because basically as they are moving towards the walls, their energy will be reduced, so they will exert less pressure. And then we calculate the energy. Then we looked at the other limit, what happens when we go to the lower temperatures. We said that, okay, well, basically we didn't really start with saying high temperature, low temperature, but we said that what happens when Z is small. Z small is essentially n lambda cubed. Remember, this is Z if n lambda cubed is much, much less than 1. And this corresponds to one way of obtaining n lambda cube much, much less than 1 is when we are at high temperature. For a given n and v, there is a critical temperature above there is a temperature above which this number is very small. So that is why we are saying high temperature limit. Then the other extreme is when z is close to 1. Well, z close to 1 basically means that there is a mu equal to 0 almost. Remember, z is e to the power mu over kt. So mu is very close to 0. And then we looked at what happens to the system. And if you remember from our earlier discussions, we said that there is an N0, which is essentially 1 over Z minus 1 minus 1. This is the number of particles in the ground state. So as long as Z is far away from 1, as long as Z is not close to 1, this number is a reasonable number, not large, not small, but we have a macroscopic number of particles, but in the ground state we have, 5 or 10 particles, let's say. Basically, they don't influence the properties of my system. But when Z becomes close to 1, that is when chemical potential is close to 0, this number diverges, essentially. And it can become of the order of n. And in fact, this is how it changes, how N0 changes as a function of temperature. You said T is equal to T critical, it just starts getting non-zero values. At T equals to 0, it is equal to N. So this is what we call Bose-Einstein condensation. And we calculated various thermodynamic properties. And well, we didn't explicitly calculate. There is a discontinuity. There is a okay. So this we can calculate how CV changes. There is a discontinuity in the derivative of CV. So again, here you also see that there is a non-analytical behavior. You see, when you look at phase transition, there is essentially non-analytical behavior in thermodynamic properties. It might be that thermodynamic properties are discontinuous themselves. That is what we call the first order phase transition, or it might be that their derivatives might be discontinuous. They can be continuously changing, like CV for the ideal Bose gas, it changes continuously, but the derivative is not continuous. So that is why it's called the second order. Well, historically, we had the second order phase transitions where when the second derivatives were 0, were discontinuous, Then the third order transition is if the third derivatives are discontinuous, etc. But nowadays, any phase transition in which second or higher order derivatives are discontinuous is called a second order phase transition. And this specific over here is a real system, the superfluid helium, and it's called a lambda transition. So basically there what happens is you have a liquid system and made up of bosons. When you have a superfluid helium, you have to also distinguish between helium-3 and helium-4, basically because one is a fermion, the other one is a boson. It will behave they behave differently. And if you look at helium-4, it becomes a superfluid. All the helium molecules are in the ground state, and as they flow, they cannot dissipate energy. So they flow without any viscosity, like superconductivity in electricity. And of course, when you, do we have such a discontinuous specific heat? Well, we didn't look at it explicitly, but if you look at a realistic case, how do you create a Bose-Einstein condensate? You see, you have to cool your system very fast to very low temperatures. So practically, if it touches anything, it will absorb heat. We don't have so good insulators, so you kind of isolate them in vacuum. You suspend them by laser light, and you even cool them by laser light. So the idea is you shine laser light to your system, and you adjust the frequency such that the laser you are using has a frequency just below the transition frequency, so only atoms moving towards your laser will be able to absorb it. When they absorb it, they slow down, so that is, they are getting colder. And when they emit the energy they absorb, they will basically emit it in arbitrary directions. So the atoms moving in a particular direction will slow down and just acquire momentum in slightly different direction, but still the net result is they will lose energy, and hence the system will cool down. Of course, the first thing you have to calculate to look at this realistic case is what happens to you have to obtain the density of states, because basically the things we are doing are just summing over single particle states. That is what we have to calculate, and for that we need this density of states in order to convert those summations into integrations. And once we have that, well, you can basically calculate all your thermodynamic quantities and study what happens at low temperature. And well, this is the definition of the density of states. If you integrate this over epsilon, you just obtain the number of states over epsilon over a range. Due to that Dirac delta, it will just give you the number of states within that energy range. And well, we didn't go into the detail. Well, you see, it makes a nice exam question, for example. Fill in the gaps.
Did you give a definition for the crossover? I saw that there was a headline for the crossover.
I just mentioned it. I didn't really quantify it. You see, the idea is, if you look at this specific heat, okay, the derivative is discontinuous. If you take the derivative once more of a discontinuous function, it's a Dirac delta. Or discontinuity is just you have a jump. Suddenly your value changes from one value to the other value. Typically this happens only in the limit n goes to infinity. You see, we are calculating partition function. Everything is analytical over there. The exponential is an analytical, probably the most analytical function that you can think of. The reason why we get these discontinuities is not due to those sums, but in the limit, those sums are all analytical. But only when you take certain limits, like n goes to infinity, your analytical function, the limit of your analytical functions becomes a non-analytical function. The limit is non-analytical. So that's why we have all these non-analyticity in the large n limit, in the thermodynamic limit. Well, this kind of creates a problem because what we call crossover is not a discontinuity, but it is a rapid change. Continuous, but rapid.
What's the difference between the first order phase transition and the crossover?
Well, first order transition is a discontinuity.
Still, I thought the second order.
Second order is a discontinuity in the derivatives. second, or in the derivative, or the second derivative, or the third derivative. So there's still, if you have a phase transition, there is a discontinuity in the thermodynamic limit. Crossover is, there is no discontinuity but a rapid change. Well, this is kind of problematic from an experimental perspective.
So it's like a finite size effect. It's like a finite size effect.
Well, you see, if you have a finite size system, it won't have a discontinuity, but it will have a crossover. But you can have crossovers even in the thermodynamic limit. There are no phase transitions in those systems.
But do you specify an order parameter for the two regions?
Well, how do you define an order parameter?
I'm asking in the case of the crossover, if you can do that or not.
Yeah, you see, order parameter is something that parameterizes your phase transition. Well, so you can define things, but how do you know it's an order parameter?
If it's something in one phase and another in another phase.
Oh, you started already talking about phases. If you have a crossover, how do you separate those two? Well, experimentally, it's even more problematic because experimentally we have error bars, we have finite systems, so it's always a crossover. And of course, does it make sense whether something is a crossover of a phase transition? To distinguish these two is really so important. It might be, it might not be. So you see, for example, if you look at a Bose-Einstein condensation, it, in an harmonic trap, it predicts phase transition. How can you show it experimentally? Your experiment will show it's a crossover because it's finite.
But crossover doesn't mean necessarily it's a phase transition.
Yeah. Now, any questions up to here?
Sorry, a rapid change of the thermodynamic quantity it should be like the scaling laws change, right?
You see, when you are talking about scaling laws, you are talking about phase transitions, right? Not
Yes.
crossovers.
Sorry?
You are not talking about crossovers anymore. You don't have scaling transitions for crossovers. Okay, so today I would like to discuss two topics. We have the black body radiation and sound waves. So let's start with the black body radiation. And since you have your exam, let's reverse the roles. You tell me what to do. So we would like to study the black body radiation. First of all, what do you understand from black body radiation?
Absorbs the radiation and then just goes.
Okay, so we are looking at an object which absorbs all the radiation incident on it. So this is our box typically. There's a hole over there. You see, the black body is this hole. This is our black body. Not the electromagnetic radiation inside this box, but that hole is our black body. So let's first clarify that. Now, so why does it emit radiation? Well, there is a radiation inside the box which exits. Okay, so if we want to study that hole, or the radiation emitted by that hole, well, we should first study what is the radiation inside this box. So how do you propose we proceed? What is my system? I'm looking at the electromagnetic radiation inside the box.
So, emitted one? Emitted radiation?
No, I'm not. You see, if I want to study the emitted radiation by the black body, that hole over there, I should look at the radiation inside.
I'm talking about the inside of the box.
Okay.
So it may emit some light radiation.
Okay.
So are we taking the Are we carrying the inside part of this or just?
Yeah, I'm looking at the inside. You see, inside there will be radiation in equilibrium with the walls of the box. So I'm looking at the radiation inside the box. How can I study the thermodynamics of the radiation inside the box? That's my question.
I'll put it in a calorie meter.
Okay, so that is the wall.
Yeah, calorie meter inside.
Okay, that is still a part of the wall. It's not the radiation. I would like to study the statistics of the radiation itself. Okay. Now, theoretically, we will look at the statistics using the math tools that we have developed.
Photon gas?
Well, one picture is a photon gas. Electromagnetic waves. Another picture is the EM waves. Well, let's look at the electromagnetic waves. So we know it's a wave phenomena. So there's something oscillating. We can talk about the normal modes of the system. Just like the harmonic oscillator we have discussed. So we know the energy levels. There are various frequencies available, and each frequency, let me call that omega s, can have an energy given by this number. How many oscillators do we have in the electromagnetic field? Infinitely many. So, well, I mean, we are interested in sums. The sums can still be finite. And each one of these modes will have this energy. So let's look at the partition function of one of the oscillators. Remember, we have an oscillator, infinitely many of them. It is in contact with a heat bath at temperature T. How can we calculate the, let's say, one particle partition function? One oscillator partition function is
Summation e to the power.
let's ignore the ground point, 0 point energy, e to the power minus beta h bar omega s raised to the power n. This is for a single oscillator. And from 0 to infinity. And this is
So this expression,
hmm,
power minus.
what is the average number of what is the average energy of this system? How can we calculate the average energy?
Minus tau Q or without beta.
Yeah, you see, are we in canonical, microcanonical, grand canonical ensemble? This is canonical ensemble. So in the canonical ensemble, we have the free energy, which is minus kT logarithm of Q1 of S. Entropy, dF by dt minus energy, or free energy is U minus Ts, or U is equal to F plus Ts, which is F minus T dF by dt minus T squared 1 over T dF by dt minus F times 1 over T squared, which is minus T squared del by del T of F over T. This is the energy of the system. So U is minus T squared or plus T squared K derivative with respect to temperature of logarithm of Q1S. K T squared, this is U1S, the energy of this S oscillator. Logarithm of Q1S will be beta H bar omega S. This is our QS. Or let me just use this one. Minus logarithm of 1 minus e to power minus beta H bar omega. Well, this is minus, okay, let me, KT squared minus 1 if I take the derivative. Well, I need to take the derivative of the inside the logarithm with respect to t. There is a minus 1 over here, another minus 1 over here. They will cancel, but the derivative of beta with respect to t will bring me another minus 1 over kt squared e to power minus beta h bar omega divided by 1 minus e to power minus beta h bar omega. Well, kt squares cancel, minus 1's cancel. This is h bar omega 1 over 1 e to power beta h bar omega minus 1. So does this look familiar? You see that factor 1 over e to power beta h bar omega minus 1. It should already remind you something. And just a hint, we are looking at an ideal boson gas. That is the chapter.
Beta H bar omega is that for this case?
Bose-Einstein distribution was given by of a given energy epsilon is e to power beta epsilon minus mu minus 1. That's nothing but Bose-Einstein condensate, Bose-Einstein distribution. But with mu is equal to 0. Remember, h bar omega is nothing but the energy of the oscillator, the energy quantum of the oscillator. There is no mu, so it's as if mu is equal to 0. And then we can talk about the total energy of the system, which will be sum over all the states of these electromagnetic oscillators, h bar omega s 1 over e to power beta h bar omega s minus 1. Okay, then we will proceed later on. This is, let's say, we assume that it's a photon gas. No, not a photon gas. It's a collection of electromagnetic waves. Just treating the electromagnetic field as a collection of electromagnetic waves of a frequency omega. Then we just quantize the system, and this is what the energy of the whole electromagnetic field is. Now let's treat it as a photon gas. Now photons are nothing but the quanta of the electromagnetic field. They have energy h bar omega. They are massless, they don't have any mass, and they have spin 1, but only 2 spin states. You see, typically if you have a spin 1 object, it has 3 spin states, but if they are massless, then they don't get all the states, they only have the maximum states. The S spin 1 massless spin 1 particle only have S that is equal to +1 or -1 states. Or if you would like to compare it to electromagnetic theory, you have seen that electromagnetic waves are transversal waves. They can be polarized in 2 different directions. x or y perpendicular to the propagation direction. So those are the two different degrees of freedom corresponding to the same omega, or you can say that they can be left-handed polarized or right-handed polarized. At the end of the day, these all correspond to only two different spin states of the photon. And then it's kind of straightforward. You see, and we have already studied the boson gas. So the number of photons in a given state with energy epsilon will be given by e to power 1 over e to power beta h bar omega s minus 1 minus mu, where what happened to mu? We already know the answer. Over here, the result should be that, but if we treat it as a photon gas, a gas of bosons, we have to somehow find mu. What happened to it? So what do you know about photons? Come on, the majority of you are particle physicists. No? You have heard of photons, or how do you create photons?
Anyways,
Tell me one.
pair annihilation like this.
No, pair.
Observations. Pair annihilation like
Okay, fine. You can create two photons by pair annihilation. Anything else?
This mu is chemical potential, right?
Yeah.
And maybe kinetic effect.
No. First I am interested in how do you obtain photons? Transitions. Yeah. So if you have an excited atom, if it is de-excited, it emits a photon. So what happens to the number of photons? It changes. Okay. Remember, where did we obtain, how did we get mu in the canonical, in the microcanonical treatment of the boson gas? Do you remember how we obtained that mu? Why we had to introduce mu?
The number of the atoms were changing.
The number of particles were not changing. That's why we had to introduce it as a constraint.
This reaction, like quite dependent on the reaction side.
No, you see, in the microcanonical ensemble, we don't have particle exchange. So we are looking at a system of phonons, of bosons, but we still had to introduce, if you remember, we had to count the number of microstates with the constraints sum of ni should be the total number of particles, and sum of ni epsilon I should be the total energy. So this was the problem. If you remember, we had created these, divided our states into different cells, and we just exchanged the particles within the cell. We had all these combinatoric factors, and from that we recovered the Bose-Einstein and Fermi-Dirac distributions. And well, how do we deal with? And we had to maximize the most probable distribution of particles among the microstates. And we had to maximize our function subject to these constraints. And how do we do that? We had to introduce the Lagrange multipliers. One of those Lagrange multipliers was alpha, the chemical mu over the chemical potential. And that alpha Lagrange multiplier, we had to introduce it to impose the constraint on the number of particles. Well, if you don't have a constraint on the number of particles, well, you don't introduce alpha. So there's no chemical potential. So that's essentially corresponds to the case mu is equal to 0. So if you don't have particle number conservation in any way, that basically corresponds to 0 chemical potential. For photons, you don't have particle number conservation. They can be absorbed, they can be created one by one. So we don't have that constraint. Now, another way of seeing that is that chemical potential had to be 0. So we are now, that is in this problem, we are looking at a system at a fixed temperature. And the system just can do anything it wants Just like in an isolated system, the entropy is maximized. If we have a system which is in contact with a heat bath and everything else is isolated, we don't allow anything else to change, just in that case, well, the free energy is minimized. So if the number of particles can change in our system, which is kept at constant temperature, then we have to minimize the free energy in equilibrium. In equilibrium, this has to be 0. Because we don't have fixed number of particles, so the number of particles is free to change. In equilibrium, the system will change whatever it can change, such that it will minimize the free energy. Well, the number can change, so we have to determine the number of particles by requiring that the free energy is minimized by the given number of particles. Well, what is the derivative of the free energy with respect to n for an arbitrary thermodynamic system? Well, remember dF is minus S dt minus P dV. Just a reminder, work is not V dP. Because in your midterms there are a couple of you who wrote W is equal to V dP. In general, it's not true. Work is, in general, minus P dV. And in general, they are different things. Anyway, so dF is minus S dt minus P dV plus mu dN. So derivative of free energy with respect to n at constant temperature and volume, this is nothing but the chemical potential of the system. So if you don't have fixed number of particles, so the number of particles is determined by the requirement of the minimization of the free energy with respect to n, the number of particles, then the chemical potential again has to be 0. So in that case, if mu is equal to 0, this is just 1 over e to power beta h bar omega minus 1. Well, effectively you recover this expression, whatever you do, whether you treat your system as a collection of oscillators or you treat your system as a collection of photons, which are bosons, basically we get the same answer. Well, we should, if our descriptions are correct, because we are basically describing the same system from two different perspectives, but it's the same system. Now let's look at this sum over S. How can we sum over the states? You can treat it as a collection of photons or a collection of waves, whichever one you prefer. What can I do? What do you propose? So how can we sum over the single particle microstates and write it as an integral? Any suggestions? Which is dp dq divided by h cubed, if you like. Now this is fine. Well, I would like to relate this somehow to lambda and omega. I would like to do both of them. Express it in terms of lambda and express it in terms of frequency. Well, d cubed q will give me v. So how can I relate p to omega? Let's start with that one. How is p related to omega for a photon? H bar omega is P. Do you agree? Do you agree because you think it's right? Do you agree because somebody said that it is right? Or do you agree because of the peer pressure?
H bar omega shouldn't it be energy?
Yeah. H bar omega is energy. P is not energy. So it cannot be correct. So what are we missing?
Divide by C.
Huh?
Divide by C.
Divide by C.
Will that just
Again, the same question applies. Do you agree because somebody said that it should be this way? Or do you agree it is correct? Or do you agree because of peer pressure?
Do you still do not hold as
Yes.
does it?
You see?
I mean, you divide it the wrong side.
Okay. Yeah. Or P, H bar omega over C. H bar omega is PC.
But with all due respect, I have no clarification of this. C is dimensions.
But you should be able to put the C's back in place when you want some numbers, right? Or you say that you don't care about numbers.
I'm a little heartbroken.
So what should I do? Should I just say that this is equal to
You can separate the radial part and then
V over H cubed? 4 pi is the radial part, the P squared, or this is V over H. H is 2 pi H bar cubed, 4 pi times H bar over C, the omega squared, omega changes from 0 to infinity. Okay, there's still one thing I forgot. You see, for a given P and Q, do I have 2 states or 1 state or 3 states?
2 because of the correlations.
2. Well, you can, let me also make a couple of changes. This is still the correct answer. But you cannot really talk about photons being in this place or that place. So let's just V straight away. Just write down the wave equation. If you write it down, basically that dqp becomes a integral over the wave vector, but the V is V. There's a 2, there's a 2. So if you make the simplifications, this is cubed V over pi squared C cubed from 0 to infinity dw, w squared. So GW, the density of states per frequency, is V over pi squared C cubed omega squared. Well, if I would like to write this in terms of lambda, how can I relate omega to lambda?
More wavelengths.
No, I have a wave with a given frequency. Omega, you know the speed. C, what is its wavelength? Hmm? You mean HC over lambda? So you are saying that as long as whatever way,
There's something else at the frequency side of that.
you see, we can talk about the frequency and the wavelength of any wave, even the waves on the sea. So we cannot have H bar over there. So forget about H. So what's the relation between omega and lambda? You see, this is just wave mechanics.
Yeah,
Hmm?
you need the 2 pi, you still need the 2
What is the, if you don't remember the expression directly, what is the period of this oscillation? You see, omega is the angular velocity. So in one period, the angle changes, whatever angle it is, it changes by 2 pi, so 2 pi over omega is the period. During one period, how much does the wave travel? It's moving at the speed of light c. So if this is the period, it moves this much. During one period, it has to move one wavelength. So this is the relationship between lambda, c, and omega, or this is c over nu. So basically, you can solve for omega and put it over here, and that will give you the density of states in terms of omega. Now, what is the energy of this system? Energy per volume. Well, this is basically, now let me write this as V times the density of states, so that I don't want to carry around the V. I will be talking about the densities all the time. So this will be the omega, g omega, h bar omega divided by e to power beta h bar omega minus 1. This is the density of the electromagnetic radiation inside our box. Omega changes from 0 to infinity. And you can say that, okay, we already know what, let me just call this whole expression as du. Du by d omega, the energy density per frequency, will be given by omega squared divided by pi squared c cubed h bar omega divided by e to power beta h bar omega minus 1. Well, this is the spectra of black body radiation, which kind of, if you like, started the quantum revolution. So first understanding this, where this formula comes from, Planck obtained this expression first, and he was unavoidably led to the quanta of photons, quanta of electromagnetic light, electromagnetic radiation. Now the question is, okay, what is that integral? You see, that integral can be evaluated. U is equal to, from 0 to infinity, dw omega squared divided by pi squared c cubed h bar omega divided by e to power beta h bar omega minus 1. And let me just make a change of variable. I will call, instead of omega, I will call omega is equal to x over beta h bar. So that u will be 1 over beta h bar cubed from dw omega. Well, there's another h bar omega to the fourth power. There's an h bar from the h bar omega inside the integral. I have from 0 to infinity dx x cubed divided by e to power x minus 1. So effectively, this is, u is proportional to t to the 4 because of 1 over beta to the 4. And the proportionality constant just depends on h bar pi and that integral over there. That integral is just a number. Now let's go back to our black body. You see, we know the energy density inside that box. Now the question is, how much of it is emitted through the box, through that hole per unit area, per unit time? You see, not all the radiation inside the box is coming out of the box. Only those that are directed towards my hole from somewhere will exit from my box. So for an observer who observes that hole as a black body, That will be the radiation he will see. And if you calculate that per area, this turns out to be C over 4U, which is again proportional to T to the 4. This is the, in fact, let me just write it as this one. Sigma times T to the 4. Sigma is all the factors over here, C over 4, H bars, pi's, and this integral over there. That sigma is the Stefan Boltzmann. Now, what about the pressure of this black body? What can you say about the pressure inside this box?
Hocam, what you asked before writing this was a little tight at some point, but this is not.
What do you mean?
What you asked was per unit area per unit time.
That is power. Energy emitted per
Yes.
unit time is power.
The equations right-hand side is not related to time.
That's power is constant. The total energy, the total energy emitted by the black body will be increased linearly with time, as long as we keep the temperature fixed. But the power, which is the energy emitted per unit time, is just a constant.
So this is still a parenthesis of t when you look at the grand scheme of things. This is per unit time.
Yes,
Okay.
that is the definition of power. Now let's calculate the pressure. How do we calculate the pressure of an ideal gas? Ideal bosonic gas. Okay, now everybody is busy. So what do you remember about our pressure computations? How did we calculate the pressure in our previous problems?
Can't we just take the derivative which is with respect to volume,
Of what?
free
Okay, right. So you are saying that let's calculate the free energy. Then you are saying that the number is fixed. But the number, so this free energy is what we obtain. Let's see, if we have oscillators, we have a fixed number of oscillators. Free energy is something we studied when we are looking at canonical ensemble. The number is fixed. The number of photons is not fixed, but the number of oscillators is fixed, so that is fine. So we are basically looking at this problem as a collection of oscillators, right?
If the number of photons are not fixed,
Mhm.
the number of oscillators being fixed, isn't the photon just oscillating back and forth in the black body? Is the oscillator?
You see, just like imagine the oscillator, classical, not a quantum oscillator, just a mass hanging on top of the pendulum. You have one oscillator. But this oscillator can contain many energy quanta. Each one of those quanta are what we call photons, and in sound waves, that is what we will call phonons. So the number of quanta and the number of oscillators, they are not related to each other. I can have one oscillator that contains 50 quanta. The same oscillator can contain 5 quanta. The energy of an oscillator was h bar omega times n. This is the number of quantum, the quantum number of the oscillator. So that is why, although we have one oscillator, in the one oscillator I can have 5 quanta, 10 quanta, 50 quanta.
So can we answer the question of like how many oscillators that are inside the box?
Mhm.
How many?
Well, we know at least the number of oscillators per volume per frequency range. T omega, this is omega squared divided by pi squared C cubed.
And this is the number.
Density of oscillators. If you ask me the number, that is infinite. I have infinitely many oscillators per volume. But that doesn't cause me a problem because of the quantization of energy levels. You see, if you plot the C over 4u omega, or lambda, as a function of lambda, well, this is the black body spectrum. And, no, omega. For example, if you would use this density of states and use the classical equipartition theorem, which states that for each degree of freedom, well, in this case we have for each oscillator, I have 2 degrees of freedom, there is an energy of kT. You will see that this function should diverge. This is so-called ultraviolet catastrophe. If you don't take the quantum nature of these oscillators, that the energy values should be discrete, then you don't reproduce the blackbody radiation. Because there are infinitely many, because equipartition theorem tells me that every mode has the same same energy, has the same thermal energy, but there are infinitely many modes in ultraviolet limit. So the system should have infinite energy, which it doesn't. Okay, so we are looking at this problem from the perspective of we have many oscillators. Each one of these oscillators have, each single one has the partition function given by this expression over here. So for all the oscillators we have, this will be sum over all the oscillators. Now, there are infinitely many terms here. Q1 of S. Just I'm summing over all the oscillators. Well, then free energy will be minus beta logarithm of Q. No, sorry. Minus KT times logarithm of Q, which will be minus KT times sum over logarithm of Q1S, which will be KT times sum over S, this is the free energy, of logarithm of 1 minus e to power minus beta h bar omega S, which will be kT times v times the omega from 0 to infinity omega squared divided by pi squared c cubed logarithm of 1 minus e to power minus beta h bar omega S. Pressure was minus the derivative of free energy with respect to temperature. No, sorry, with respect to volume. Well, which is minus KT logarithm of 1 minus e to power minus beta h bar omega S. Well, let me also write it in a slightly different form. This is PV divided by KT is equal to minus 0 to infinity GW V dW GW logarithm of 1 minus e to power minus beta h bar omega S, which is nothing but minus sum over all single particle states of logarithm of 1 minus e to power minus beta h bar omega S. Well, which is essentially minus logarithm of the grand canonical partition function. Well, sorry, not minus. That is the grand canonical partition function for a gas of photons, which are bosons, with chemical potential set equal to 0. So even if we started with in the canonical ensemble, a set of harmonic oscillators, well, infinitely many of them, but still a set of harmonic oscillators, and now we recover the final expression we obtain is the same as if we had just looked at this problem as a collection of identical photons with chemical potential 0. Well, then, of course, evaluating the integral, you can find how the pressure changes with temperature, but just I would like to mention one thing. Let me take this one. Okay, one thing you should note here is pressure depends only on the temperature. The thermal radiation has a pressure which is independent of the volume. It only, well, just like as if it's during a phase transition, the pressure depends only on the temperature and not on the volume. Any questions?
So I'm a bit confused about what is conserved and what is not. So the total number of harmonic oscillators is conserved, right?
Yes.
So what is not conserved?
The number of photons.
Okay, so we start with canonical ensemble using the harmonic oscillators and then arrive at grand canonical ensemble of photons or something.
Yes, basically we have two different descriptions of the same system. As a collection of harmonic oscillators, where the number of harmonic oscillators is fixed, but they can be excited, de-excited, etc. Or a collection of photons, whose numbers can change. What are photons? Well, photons are the energy quanta of the oscillators. So excitation of oscillators or de-excitation of oscillators basically corresponds to changing number of photons. Now the photons can easily be created. So there's no conservation law on the number of photons. You see, we looked at the chemical reactions, for example. In chemical reactions, the number of reactants are also not conserved there. But still, there has to be a relation between the number of reactants, the number of chemicals we have. There is a constraint over there. But we don't even have such a constraint in the case of photons. There, you can freely change the number of photons. And since you can freely change the number of photons is determined by the minimization of the free energy, which means that the chemical potential has to be 0 for photons. So photon number is not fixed, so photons have chemical potential 0. Harmonic oscillators, their number is fixed, so in a sense it's in the canonical ensemble.
So we could have as well started with grand canonical ensemble with photons, right?
Yes, you see, if you look at this expression over here, this one, when we were looking at identical particles, we had already shown that PV over KT is equal to 1 over A sum over the logarithm of 1 minus e to power minus beta h bar minus beta epsilon minus mu. There's an A over here. You see, this we had already derived for a general system. There's a minus sign over here. A was 1 for bosons, minus 1 for fermions, and 0 for Maxwell-Boltzmann. You take the limit as A goes to 0. And compare it with did I write it somewhere? No. Compare it with this one. This is for general ideal gas. A is equal to 1 for bosons, -1 for fermions, and 0 for Maxwell-Boltzmann distribution. Well, this is for a gas of bosons with mu is equal to 0. So basically, a collection of oscillators with a fixed number of oscillators is the same thing as a collection of these energy quanta, where the number of energy quanta is not fixed, is not conserved. So let's give, yes.
I'm not convinced that these are two different methods. I mean, treating and talking gas oscillators.
I'm starting with different assumptions to start with.
But then after some point we are just performing the same stuff.
Sure, because after a couple of steps, our expressions are the same. Just the interpretation is slightly different. And at the end of the day, since both interpretations are interpretations of the given, of the same system, they should also lead to the same results. Just this black closed box doesn't really care how you interpret it. So as long as your interpretation is correct, you should get the same answer. Anyway, let's give a 10-minute break, just 10 minutes. And then we will continue with the sound. It will be essentially the same treatments, just a collection of oscillators. In that case, in the case of sound waves, it's a collection of finite number of oscillators in a solid, where the atoms are vibrating.